in a panic because people still don't have a good idea to how to avoid this problem. I mean, there's various defenses proposed, mitigations, but no one's got a foolproof method that actually gets rid of this problem in general. And this affects almost any domain where neural networks are applied. Natural language processing, image processing, discrete domain simulation, when you're trying to simulate physics models, the same problem happens, very small perturbations. So the property that we want in this trait is that small changes in the input should result in small changes in the output of a function. It should be robust, is what we say. And you can come up, I mean, the devil in the detail is what you mean by small, and that's a hard problem. So that's a subfield in its own right. But a very naive definition is that you say, well, if F is a neural network and you have some input image X and some values epsilon delta, then the network is epsilon delta robust around the original input X. If for any X that is within epsilon of your original image, then the output of the neural network is on the original image versus the new image is less than delta. Hopefully uncontroversial. Obviously, you have to define a distance function. But there can, of course, be controversy if...
Question?
Yeah.
So these are differentiable functions, right?
Yes.
So they're in particular continuous. So it is true that for every epsilon, there's going to be a delta that makes epsilon delta robust.
Yes, they're nearly everywhere continuous. They're not completely continuous.
Sure, so it's nearly everywhere robust.
Yeah.
Yeah. So then you kind of want to choose the delta independently of the epsilon.
You absolutely do, yes.
Okay.
And coming up with good ways for doing that is still what happens is that they tend to, depending on your domain and your exact distance function, you kind of see how far you can push the verification, or see how big you can make epsilon and delta. And if you're generating images that really are indistinguishable, then you're probably okay. And if your epsilon is too big.
Oh, sorry, I mixed this one. Maybe delta like this.
But yes, it's a good point. This isn't a free lunch. Like, this isn't a definitive. This is what you want to verify. There's a lot of parameters that you have to tune. But this is what the neural network verification community has spent a huge amount of effort on in the last 7 years. Is looking at this property for various definitions of small. What are some other sources of properties? Sometimes neural networks are used to approximate standard algorithms. Mainly for performance reasons. Your standard algorithm may be too expensive to compute, or it may be doesn't fit on disk, as we'll see. So it's good to put the neural network compresses the original algorithm in some sense, and we can derive properties that we want of the neural network from the original algorithm specification. And the classic example of this is ACAS-Zoo, which is a autonomous aircraft controller that is deployed by, it's not NASA, it's Federal Aerospace in the US somewhere, I think. But it's a real system. It's for autonomous vehicles, and you have autonomous aircraft, and you have 5 inputs in the simplified model. The distance to intruder, angle to intruder. Intruder is the other aircraft that you've detected. Intruder heading, speed, and the intruder speed. And you output, no problem, clear conflict. You don't have to do any evasive action. You need to turn strong left, strong right, weak left, weak right. So fairly simple. And this system was originally implemented as a 2 GB lookup table with all possible, well, highly discretized the state space and gave an answer for every possible value. But this was actually replaced with a neural network in order to improve size and latency requirements from the system, because it needs to fit on very limited hardware. And the properties are just taken from a lookup table in this case, and there's the experts, the aerospace experts, sat down and came up with 10 different properties. And this, for example, is property 3, which says that if the intruder, if the other aircraft that's kind of threatening you is directly ahead of you and moving towards you, then you definitely don't want to advise clear conflict. So you don't know what you should advise, like you don't know what the optimal action actually is, but you shouldn't be saying you don't have to do anything. So you can write down a formal specification for this. Yeah. Existential just says that there exists an action. So strong left, left, right, strong right. One of them is the score for that is of the neural network F is greater than the clear conflict score on the bottom right. Any questions on seems plausible as something you might want to verify with the system? But because there's 10 properties. And they literally named them, they didn't have meaningful names, they just said property 1, property 2, property 3, property 4. It's a good question. I mean, in the vehicle specification version of this, we've named it directly ahead and moving towards size not minimal. Yeah, oh, maybe we did call it property 3. Yeah. Directly approaching. Sensible directly approach. Yeah, I don't know.
Or maybe it's the minimum clear conflicts for when it can be minimum.
Yeah.
Yeah, I don't know. Not only, but it's a good question. So in what talks about them we can use the main apparently that's how they work. So the engineers give them as a few properties like this without particular specification. It's just it's a domain knowledge that these properties should be there. And those who verify, like in this case, like our system, they just translate this into terms of the logic without again thinking because they're not the main experts to think about this. So, yeah, a lot of in this domain is kind of like this sometimes with questions like this because of the separation issues. The engineers did know communication problem, applications don't know the domain, and so everyone just keeps everything frozen, feel free to touch anything.
Thanks.
And finally, I guess property 3 is domain-specific properties. So ones where they're really hyper-localized to your domain and they don't transfer very well. But a nice one might be, for example, considering if you're trying to approximate some fluid simulation, terribly expensive to compute exactly or impossible to compute exactly, but the neural network might be able to approximate it. You don't know what the neural network should do exactly, but you know that physical laws should be obeyed. So you should have conservation of energy. Your simulation should conserve energy in its predictions, for example. It's a bit.
We can lie, but don't tell me about like can catch you in the lie. It's not really doing any kind of physical simulation.
No, it's not. No,
it's very far from it. But it's just you can't catch it on the invariance.
Yes, yeah, exactly. It should respect the invariance. I mean, and it's never going to be. I mean, it's never going to be accurate. It's never going to be 100% accurate, right? You just need something. You're just interested in something that you can compute in 100th of a second, in real time. That is going to give you an approximation of what's going on. But you would like it. You'd like that approximation to be sensible.
But sorry,
yeah.
So if you're trying to model fluidity, right? That's subject to some differential equations.
Yeah.
So once you have found the minimum network, but you try to solve the equation up to some.
Yes, but I mean, in practice, those equations for simple models, maybe straight tube, then yeah, it's possible that you could. I think it quickly gets to the point where the solutions. I mean, it's really hard to even solve the equations, right?
It's hard to solve. If you have a solution, you can try to show.
Oh right, okay. Yes, yeah, yeah, that's something possible. Depending on how nonlinear the property is as well, because these verifiers are. As we all get on, they're not all powerful. They can't verify arbitrary properties. But
this okay for interruptions.
Huh?
Interruptions okay.
Interruptions are absolutely okay. No, interruptions are good. Okay. No, go for it. More interruptions the better. Yeah, okay. So that's the source of that's 3 different sources of properties that we might want. So hopefully I've convinced you that there are actually interesting problems out there and places where we do have specifications that we actually want to check that our neural network verifies. So just going to talk about verification for a second. So there's a whole range of domain-specific verifiers have popped up like daisies over the past 7 years, spurred mainly by this adversarial robustness example, because that really panicked. Before maybe 10 years ago now, everyone thought that neural networks were actually reasonably good solutions, and that they were learning the actual something semantic underneath. But the fact that these counterexamples existed, small perturbations of noise, shows that actually they're not succeeding at perhaps learning the semantics of the domain as well as they would hope. So one of the big ones is Marabou, which is based on SMT technology. So it encodes a neural network as a giant SMT problem, a lot of different constraints for all the layers, and each individual node is encoded as a constraint, and then it munges with some domain-specific heuristics and exploiting the symmetry of the neural network and things like that. There's things like Aaron, which is based on abstract interpretation and mixed integer linear programming. Verisig interval arithmetic, the current most highly performant one, which is alpha beta crown, which is linear bound propagation, and there's various international standards and competitions for evaluating these solvers. We really like Marabou because it's the most expressive. I mean, SMT, these things, interval arithmetic, abstract interpretation stuff can only really verify input regions mapped to output regions of the network, whereas Marabou is much more expressive. Yes, and the set of inexpressible queries is large. Okay, so suppose we have this property. What is actually the process that we go through to try and verify a neural network? And it's a bit different from standard software in some sense, because the software artifact that you're trying to verify, you can mutate and modify as much as you want. You're not wedded to a particular implementation. You can just throw it away and retrain entirely. As long as it satisfies your spec at the end of it and the performance hasn't degraded, then you're good. So the first step is to try and train your neural network to satisfy the property, because by default it's trying to learn it from data, but you're very unlikely to have learned the spec perfectly just from your input data set. So you somehow need to feed your property into training to incorporate it. You then might do some lightweight counterexample search. If you can make your property differentiable in some sense, you can exploit gradient descent algorithm to try and find counterexamples to your property, so a falsification step. You would then try, and once you couldn't generate any counterexamples anymore, you can then chuck it to your verifier, and with Marabou or Aaron, etc. And finally, something that's not really considered in the verification community a lot, because they're all automatic theorem proving guys, is that afterwards, you'd really like to reason about your entire system that's built around your neural network as well. So if it's your controller for your autonomous car, you would really like that your neural network has some property, and then that property implies that there's some temporal safety property for your car. It never goes off the road, or it never does something crazy, no matter what sequence of events and time happens. So there's kind of larger system properties that you would like to feed in your neural network property into. And obviously there's some feedback between this. Counterexample search can inform training, and verification counterexamples verification again can inform training. So we'd like something that kind of incorporates this entire life cycle. And what are the challenges that in this, which are non-standard? I mean, obviously there's the theory challenge of trying to find appropriate verification properties in the first place. Verification itself, I mean, there's undesirability of nonlinear real arithmetic, and just the scalability of these things. The deeper and deeper your networks are, the more it's exponential growth in the number of layers in terms of time that's required to compute and solve these SAT problems. So they don't scale terribly well. Although, having said that, they really do quite impressive things. Hundreds of thousands of nodes, millions of nodes, neural networks you can verify as of the last couple of years. So not ChatGPT levels of neural networks, but real practical size neural networks that can solve real problems in the world.
And this is the phrase that we couldn't say 2 years ago when we started the project. 2 years ago,
No.
I was saying it's only very toy questions, even your standard
10,000 nodes, you know, somewhere.
You say, well, okay, ChatGPT is not, but everything else is much possible. So this has changed recently.
It has, yeah. I mean, it's super impressive how fast the verifiers are coming along. So, yeah, possible. So, machine learning challenges, understanding and integrating how to integrate properties into training. The ones that we're kind of, most interested in is programming, finding the right languages to support this cycle, and integration into complex systems that are built around the neural networks. So some of these, we looked at this, we came to this at the side project, we came to this area and we kind of did a survey of all the different techniques, and we found that actually a lot of this is really, we tried to think, okay, how would we actually do an end-to-end verification of a neural network using this cycle? And we found that actually there's a lot of problems, and a lot of them are actually just insufficient programming language or API support that makes it really difficult to do this. So we're going to have a look at some of the frameworks. So this is a training framework for specifying properties, and this is the format in which you'd specify the robustness constraint. And maybe the font is a little small, but it's a Python DSL, and actually the logic is all mixed up in the training framework code and the and kind of gory implementation detail of the framework. That it's almost impossible to read off what the specification actually is from this. I mean, there's things like x-0i.cpu.numpy, all this stuff that you just don't want in your specification. There's another training framework, ART, which is a little bit better. You at least have named parameters, and there's not quite so much implementation gore seeping into the interface. But it's still not exactly the kind of, it's still hard to go back to the ACAS-Zoo natural language spec from this particular piece of code. This is, for example, the Marabou verifier Python interface, which is again ACAS-Zoo. I mean, this is literally a list of numbers, and this is what they write when they're writing down a specification, and you just have to read off those numbers and check that it actually matches what the natural language spec says. But to the domain specific expert, they cannot check the spec, right? They can't check that the verifier person has actually encoded the constraints correctly. And this is my personal favorite. This is literally the specification in Erlang for the ACAS-Zoo. And this is what you write down in your file. So I think as programming language people, we can all agree that we can do far, far, far better than this. This should not be the ground source of truth for your neural network. Should properly do a neural network.
In this corner, we don't see the full citation, but it's awful 2019 where it is published.
And finally, this is the standard format for verifiers that has been the community is trying to converge on, which is a variant called VNNlib, but it's a variant of SMTlib. It's, as you can see, it's got some logic in there, and at least it's not implementation specific, but there's very little. It's supposed to be machine readable, as all SMT formats, and it's not supposed to be human readable. And this ACAS-Zoo network only has 5 inputs, 5 outputs. When you have a robustness specification, which is for an image processing thing, which has 10,000 inputs, 10,000 outputs, you just get a file that's just, you just have to read through 10,000.
One equation per pixel.
Yeah, one equation per pixel, and it's just not readable, not interpretable. Okay, so what are the problems that we've identified? The first one is interoperability, I guess, that we can say. So these specs, you have to write one for your training framework, you have to write one for your verification framework. You then, if you wanted to prove something about in an ITP, you'd have to then reformate the spec in an ITP. So we really, there's no guarantee that the semantics are shared. between your different versions of your specification. And it's not even obvious looking at your two specifications in your different stages that have the same specification. Interpretability, hopefully that stands for itself, but it's not easy to read off the spec and work out what the mathematical property actually is. Integration, these systems are in isolation, so you can't talk about the larger system. You can't talk about the larger system's properties in relation to property of the neural network. And finally, something that we haven't touched upon, but is kind of important, is that neural networks really work over a sequence of numbers, large vectors of numbers that you feed into neural networks. There's no algebraic data types, there's no kind of nice structure to the inputs. So whereas your verification specification should really be expressed in terms of the objects in your problem domain, semantically meaningful problem domain, and they get translated down to numbers. So actually most tools really just allow you to write specifications over the raw numbers that are fed into the neural network. So the question is, can we do better, and can we actually write down our specifications in problem domain and have our compiler tooling automatically handle that problem for us? Anyone have any comments on these, or any ones that you think that we're missing, or?
When you say integration, you don't mean integration.
I don't mean I'm afraid I don't mean integration in the mathematical sense. I mean integration into other systems that allow you to prove stuff about your widest software artifact that's built around your neural network.
But you only come to the core verifier is a black box as well, right?
The core verifier, yeah.
Verifier is a black box, and you're doing is putting the all the wires in between, all the glue in between.
That is exactly, and trying to work out, and then trying to see, yes, yeah, that's it exactly. And yes, Vickle is designed to address all these problems, and it does this via domain-specific functional language for writing the specifications, and we'll go on. It's dependently typed, has first-class instance search and things like that. Lots of really nice, which makes it very natural to write in. It provides analysis-informative error messages, because actually each of these have very different capabilities in terms of what properties they can support. So it helps to explain to the user why you can't compile a given specification down to a verifier, or why your training is going to perform badly for this particular specification. And we have, yes, analysis informative. So we've connected to the Marabou verifier down there, and we can export to TensorFlow code from your property. You can change your property in TensorFlow code so you can train with it. And at the moment, we can export to Agda, which maybe isn't the most natural system in the world to be writing proofs about neural network enhanced software in. The team has everyone on the team could use Agda, so it seemed like the best to do. But the Agda integration is maybe a 500-line file, so it's not a fundamental limitation. We can substitute for something a little bit more realistic, like Cockle Isabel or Chimera X, which is a domain-specific differentiable, domain-specific interactive improver for differential equations, dynamic systems. Cool, and should say that there are people. This is not a new idea, that you could have a unifying API. There are other tools out there, so please, if you're interested, go have a look. First of these is Socrates. You write your specification in JSON, and it can call a variety of verifiers, but actually doesn't solve any of these problems. It doesn't, that we've identified. It doesn't. There's no interoperability between different stages, because it only does verification. There's no readability. It is still very low level format. There's no integration to larger systems, and you have to write, the embedding gap is not bridged, because you still have to write your specification in terms of the raw numbers. There's a Never framework, adds training and pruning quantization. So it does. There is some interoperability between the two different specs, two different stages, but not a lot. CocoaNet, which is a neural network format. Again, it addresses some of the problems, but not all of them. And maybe the most mature competitor, which is Kaiser, which is by a group of interactive theorem proving people in France, and they use the Y3 specification language that can connect to various interactive theorem provers. So they're definitely looking at integration, and they have some interpretability, but it's reasonably high-level language. So there's interpretability, but they certainly don't have interoperation with other training frameworks, and they don't cross the embedding yet. So we aim to resolve all of these and support the communities. Support the community in trying to come up across those 5 challenges that we discussed before. And in particular, we don't look at all of them. We're certainly not trying to find vehicle doesn't magically give you verification properties. It certainly doesn't help with the verifying challenges. We lead back to the ATP community. But it certainly does help with integrating this in property-driven training. And hopefully you'll see that the language we've come up with is reasonably well-tailored to the domain and alleviates a lot of pain points. And we do integration into interactive theorem provers. You can export the specifications into interactive theorem provers, so you can really prove properties of the entire system, not just your neural network. We don't have one definitive paper on this. There are various sources. We had this year we had a publication in ICFP about compiling to general SMT solvers, but Marabou in particular. And we've had a paper on the training, on the lot theory that underlies the training. And then we have various tutorials and the user manual online as well, and the language spec. And yeah, one of the purposes of this tutorial are to discuss the challenges. So if people have ideas about where to go on some of these problems, we'd love to hear them. And understand how logic and PL semantics can contribute, and we're going to introduce the vehicle specification language, and we're hoping to get you running some examples if people are interested in doing that. Cool. Okay, so before the coffee break, we're going to have an introduction to the language, and we're going to look at the ACASU spec and robustness and how you encode them, and some of the details of the pipe checker and the vehicle compiler underneath. Some decisions we've made during the break, and after the break we're going to have an exercise session where try and get people, if they're interested, to write a vehicle specification, and then after the break we're going to have some discussion on the theory behind property-driven training and how you can take logical specifications and actually incorporate them into training, and we'll have a demo on integrating specification into Agda, and then we'll wrap up by discussing some of the application areas that we might look at. You might look at it further if you're interested. Does that sound feasible? There is setup. If you want to set up, you can clone the tutorial, which contains the specifications and the exercises. Installing vehicle itself is very easy. This is maybe the first time in ICFP ever that there has been a pip install command. It comes up on the
Unfortunately, no one sees it, so
no.
the technology will become mainstream for it.
But it is a Haskell compiler guide, compilers within the Haskell, but it's interface and all the machine learning people. But the emphasis on this has been very much how can we come up with a language that machine learning people will use and interfaces well with existing machine learning technology. So we bundle it by pip, and we have pip Python bindings. And finally, you can install the verifier, pip install Marabou, again, a single command. Okay. Yeah.
That's small group. We can really adjust to what you'd like. So if you have any comments, questions now, let us know.
Sorry, I've lost the.
Okay, so this will be a very quick introduction to the syntax, and we'll try to kill two birds with one stone, introduce the syntax, and we will formalize the equals example at the same time, so that we'll have a sense of some kind of completed task at the end of this particular section. So we'll introduce main building blocks of vehicle as a programming language, get to practice it. Yeah, right. So recap of these 4 problems. At the end of my little session, I will ask you which of these problems we have solved through this demo. So please keep your concentration going. Just a quick reminder. So this is what we're going to formalize. So Matthew has already explained this. So the neural network of this shape will have 5 inputs and 5 outputs. So this is what is being fed to the neural network. They're actually not on one with the 45 neural networks for some particular other parameters, but let's just think that we have given some magical neural network, and it will have those 5 inputs and 5 outputs. So that's the setup. Maybe since we're going to be seeing lots of Haskell-like looking code that refers to all these notions, so let's just once again have a look what it is. So for the neural network, it's important how distant the intruder is. It's going to be the raw symbol, uncle to intruder heading. So let's call it uncle to intruder theta is here, right? The distance is obvious there. Intruder heading angle is there. Own speed and intruder speed. Okay, and then the advice is clear context from that quick right, strong right. Matthew has already shown this property and this quite ugly property, then massaged down into the language of the SMT solver. Let me think if there is anything important. Perhaps the important part is what you see is, when what you didn't see in the previous slide is that all these instance to intruder angle is such and such were instantiated with some magical numbers. And they are usually in this community, as we have said, given by engineer and people who write this SMT query. Verificationists have no idea why 980 or 960. So this is kind of like some magical numbers. We'll keep on emphasizing this because this is potential source of errors, right? If the engineer suddenly wrote something else, and so if your interface becomes very ugly, those errors will be accumulating. So one of the things that we call, by making this more transparent in the syntax, we're hoping that potentially it will open the way for engineers to also spot errors if there has been some error on the interface.
Question about this. You think this probably doesn't guarantee, for example, that won't be turning into the other page, right?
Absolutely not. So you need a second property.
Right. Okay. But, I mean, if time I get a detection has to do something, I don't really get any kind of any reason why it was left or right. I don't actually know.
Well, that's the thing, right? Is that the system, if it both, what the overall system property of prove is that if 2 planes are running, then there's no situations where they will ever collide, right? But you certainly can't prove that with a neural network verifier on its own, because a neural network verifier is just an instantaneous decision input. So you need some larger, if you want to prove a real safety property, you need to connect the neural network verifier to some larger development, either an ICP and prove it formally, or we need to connect it to some reachability framework that crunches the entire input space and works out is there any.
So can you actually prove that the system property, like your river in like 10 properties?
So you absolutely, the 10 properties are absolutely not sufficient to prove that system safety property. Absolutely insufficient.
This is kind of testing on steroids, but not proof.
So
Yeah,
it's
some really big lights, but
so it's sanity checking, but crucially, I mean, this is over infinite inputs.
So yeah, so they would say it's absolutely not testing because it's axiomatic reasoning over by
But it's just not for proof that you actually, in this example, it's not proof you actually want. But in the end, at the end of the tutorial, in the last half an hour, I'm going to show you an anchor demo of a autonomous car controller that you really do, that controls a car in a noisy environment. It has some noisy sensor readings, it has wind, non-noticeable wind, and actually prove that the car never goes off the road.
So because yeah, it was one of the missions of people to make sure that we have a language that it's integratable to
Yeah,
other provers.
And then actually, we didn't think that anyone had actually managed to do this before, prove a system properly. Or very new without the system.
So you just like you've got the pull request from someone else who's using the system, or that's something you think?
No, that's something that we put together. So it's you know, it's still a toy-ish, it's not really a setting, for example, but we think it really is the first case of end-to-end system property with a chain of trust. So yeah,
Okay,
it's a developing community, they're not all the way up yet. I mean, you need a lot of domain knowledge in order to prove the safety property in this case. But yeah, it's an excellent topic.
okay, so let's start with this. So we'll forget about the larger system integration for now, and in this little section, we'll just formalize what ACAS glue people could. Actually, in that sense, we are not extending boundaries of what's verifiable. We're only now building a language on top of what people could already do in the SMT community. Okay, so we start with declaring types, and of course we declare input vector and output vector. They're both vectors of rational numbers of size 5. Is just coincidence that they're all the same size. It's small network. This is actually already an improvement, because if you have seen examples by Matthew, they had to reason in terms of each index of the vector, and here we could start reasoning about vectors as a whole, which is already a little bit of an improvement, one step up from what the SMT-lib language gives you. And then we declare a type of a network, and well, I'm gonna give it the name ACAS2 in this case, and its type is from input vector to output vector. So this is an important symbol. If you work with vehicle, and you will see a lot of this at, it usually means that there's some external interfacing happens. Maybe vehicle sends something outside, or maybe vehicle takes something in. In this case, well, is it are we shipping or are we receiving this object? What's your guess? Is it importing or exporting? It's importing, right? Because we're not going to actually define the ACAS network in the language itself. We're only declaring the type. We're hoping, or rather we will have to provide this object in the same file. And if you try to solve exercises, you will see that with every step there is a little folder that says, and this is your neural network as it was trained by Python, by someone in Python. But so this is just declaring the type, and it says, well, if you actually want to fetch the function itself, go and fetch it. And this is this at symbol sent you there.
It's a big, it seems maybe obvious to us programming people, but in other frameworks, you really do hard code the network into your spec, and you actually, yeah. It's a really poor decision, because you're no longer writing, you really don't care what the network object is, you're writing a specification over some abstract network object. But for some reason, other frameworks, I don't think are quite got that. And that you do, they kind of wire up their spec to agents, and you're not going to end up even specifying the architecture of the network in the stack, which is weird. One other thing just to say quickly is that this type synonym, I mean, the language is dependently typed. I mean, really, that just attributes to an input vector, or is a colon type. There's a very conscious decision that to hide as much of the scary dependently typed stuff. Well, to Python programmers, definitely, to machine learning people, definitely, and to hide as much of it as possible. And we actually hide an awful lot of it, and people don't use the features very much. And we will explain at the end of this why we even use all these advanced functional programming.
You have machine learning users.
We have machine learning users. We have master students.
We tortured our master students. Well, to be honest, those master students, one was stronger, the other was weaker. It's like yesterday, if you attended the report, how students switch between different languages. So those who struggled with Python actually found vehicle much easier than Python. So it's not like, oh, they get stuck because of vehicle. They actually, Python can be also very, very cryptic. So not also, but it can be very cryptic.
Also, by understanding Python programs, understanding them, but
maybe there's some truth in that. But I mean, but the dependent types that they use in this are usually just the vector size. And they have size vectors, and that scares some of them, even a couple of them. I mean, a couple of people have said, "Oh, why do you have? How can you have sizes in your vectors? Like that doesn't make sense." But that belief is what we see.
Yeah, okay. So some of the types could be inferred. You could declare a type of phi, you could just state phi like this, and a type could be inferred then. Okay, so we'll go now and see how you work with vectors, and there is a good reason to work with vectors here. The problem is the problem of the embedding gap that Matthew already mentioned, and so we'll now see the instance. So the trained Akers-Zoom network assumes that the inputs and outputs are normalized to values roughly between -2 and 2, -5 and 5, or -2 and 2.
No, it's between -1.703 and 0.92, and I have no idea why they normalize them between -1 and 1 or 0 and 1, which would be the same thing to do, but that's just what the network is right now. Which is categorized at -2.
But this is very usual for machine learning, right? They don't want to have values all over the place. They usually normalize them, maybe not -2 and 2, usually between 0 and 1. But that's the point. Usually the engineers give you some numbers, 1,680, and then they all get massaged to smaller numbers because machine learning models behave better than all numbers when vectors are scaled. Yeah, but we have specification in the original units, which are very different. And of course, by the time you give something to neural network, you forget about connection to angles, miles per second, etc. So that's the instance of problem space input space mismatch, which was a very big problem in our opinion when we found this area 3 years ago. So being able to write specifications about the problem space using the numbers that engineers gave us, and at the same time have some kind of a grip over what happens on the neural network level, distinguishes Recall from any existing verifier for neural nets. So let's have a look how this would happen in this particular example. For us, distinguish between normalized and non-normalized vectors. So let's have a type synonym. A normalized vector is also vector of size, vector rational of size 5.
That should really be a new type. We haven't got around that. So it really is the same type of previous ones, so just some kind of
Yeah, but it will just helpful. Okay. So we'll start normalizing now within the language. And so for that, we will need some notion of minimum input values, maximum input values, and then mean scaling values. And then we use some knowledge of how normalization happens. And well, actually here we use knowledge of what sort of inputs the engineers gave us and just populate these minimum and maximum and mean scaling values there.
Yeah. Is the number of decimal digits significant? That the definition of 5 and about 6 numbers after the decimal point. Is that significant?
It's not, so those numbers are what is written in the numbers given by the engineers. I wrote 6 significant figures. In practice, it's not exact because the verifiers obviously work up to some floating point precision. So the number of decimal points is significant in that sense that if you go too deep, then the verifier will become within the bound minimum. So you use my verifier and then it would normally further floating point. But it's usually 10 decimal points roughly before you start moving through the constitution. But it's a good question. So yeah, but it's and you'll notice that we're using the which stands for rational type. It's solving floating points. Floating point problems is something that we didn't really want to focus on. I mean, it's a hard enough. There's enough moving parts that we're ignoring the issue. So there are some floating point examples.
I think no one does floating points in the
Well,
almost no one.
Well, the abstract interpretation frameworks claim that they do their verifiers are sound because they over approximate input. And I don't know how much that
Someone is looking in, some
people do care about it, but it wasn't the focus for.
and when we give tutorials on verification, that's one of the common questions. And what do you do about unsoundness that that is innate?
I mean, they care a lot about nouns, so you don't want to get a noun.
Yeah. Mhm.
Because the nouns don't mean anything. Like if you
It's a step up. I mean, everyone's. It's a step up, right, from what you could do previously. I mean, yes, there are unsoundnesses lurking around, but I think the chances of you hitting them in a significant sense that it's actually going to. Yeah, I mean, it is unsound, but there's no way around that. It is unsound. But so if your neural network is obviously runs in floating point numbers, and the verification often works over reals. So if you have rounding issues or catastrophic underflow or overflow, then yeah.
but implementation is not sound differentiating between one. It's quite symbolic differentiation, but it's more or less, it's morally computing the exact function, right?
Yeah, and then you approximately map it into the floating point. You move precision. I mean, with the field of work that uses discretized neural networks, or quantized neural networks that really are just these works are in dismantling. Maybe don't have a comment, but this is the whole host of other problems that really just have.
Okay. So in a previous slide, we defined vectors concretely just by providing values, but obviously we assume people will be working with very large vectors. So there is a constructor for each that lets you run over indices and assign some values. So this is a very trivial case. We just assign 0 to every value in the vector, but we'll see a more interesting one. For example, with normalization, right? Here we also run for each of elements of the vectors, but we apply some interesting functional weight each of the values found at every index. And in particular, so let's have a look for each of the indices there. So this is a vector lookup, by the way. So if you see that, it means, well, go and fetch me the i's index in the vector x. And so for each of these indices, you have a few lookups here because mean scaling value is also vector and so maximum. And so for each of these, you go look up indexes at a certain place in each of them, and then apply this operation. So you subtract mean scaling values and divide by maximum values. But so there are 2 instances we are using for each.
So in that language, you about like this.
Yeah.
Especially if it gets implemented as a vectors or unit tests, right? So we automatically provide something we want to provide to, or is that?
So we automatically, it depends on the back end. So in the TensorFlow backend, we're doing rapid translation to synthesize arrays and then slice it over arrays. In the vector, in the query language, when we define queries, we're just normalizing. We're just immediately trying to find it. So we don't matter.
You still use 2 axes into a system.
Yes, it's true.
You really want to just sit there, just like this, it's just about the same thing.
Yes.
Yeah, it's going to have lots and lots and lots of value. That doesn't want to in practice. So this is a difficult question.
Yeah, no, I mean, it's a good question. You're right, if that would be better for performance. I guess the emphasis was on trying to mimic, well, maybe we've got the worst of both worlds. I'm going to say that the emphasis was trying to get something this convention that's Python people would understand.
Right, so that's a big event, right? Because then you can get Python people to work in this.
Yeah.
Do they? You said that it's the ones who couldn't do Python. Are very good at this point.
Yeah, she definitely found writing specs much easier than to train more neural networks.
Okay, sorry. So
No, you don't have to apologize. No, it's a great question, and you're right. In a functional language, it's more efficient, right? You know, if you were writing this.
especially the vector ones, you know, you can.
Okay, so and that was the first time we saw functions. Functions are defined as you would expect, type arguments and expressions, all involved in the usual way. This is a function of type bool, and it just checks whether your vector is normalized or not. That is, whether it's between minimum and maximum values, and we'll sometimes call them predicates if they are types as Boolean functions, Boolean value functions. No, functions with the return type bool. Okay. And another thing that's interesting that you can see on the slide and that we haven't seen before is not just that it's a function return type bool, but also that it uses for all. For all we haven't seen, we have seen on the previous slide for each. Well, Matthew would probably be able to talk a little bit more, but for all, it allows you to reason about infinite sets of values. And sometimes you can actually use it for finite and infinite. So we'll have a little bit of an exercise in the next few slides when it's for infinite and finite domain. But yeah, the main difference between for each and for all constructs is that for each will always be running over finite set, and for all may have an infinite domain. Okay, no, this is not going to have us at the next exercise. I thought I wanted to remove that. But anyway, let's just proceed with this specification because I want to hammer that down, and we're only a few lines away from actually running the verification query. So we had ACOS-XOO network already defined, but this is normalized ACOS-XOO. So this time we just say, well, this particular one will be applying ACOS-XOO to normalize the input. So we'll need it in a few seconds. You don't have to, but it just reads nicer as a spec. You could define distance to intruder, angle to intruder, and just assign them numbers because soon they'll be indices. So it will be much easier to write, go and check intruder speed rather than go and check force element of your vector. Right, so this is the main thing here. And of course, it's nice that the vehicle will keep us right, so you wouldn't be able to index into larger index than your vector permits. So there's this light sanity checking that type checking provides. Okay, property. If the intruder is directly ahead and something. So let's focus on directly ahead. And this now is very nice in the specification. It's pretty human readable or solvable. Well, numbers that we get still from the engineer, but that's basically it. So you look up the element x that stands for distance to intruder, and you check that they should be between these two values, and same for angle to intruder. And this is a property, of course, because the return type is bool. Is this all good? Okay. Then exercise for you. Can you identify whether the specification is written in terms of input space or problem space? Sorry? No. Yes. So input space is input to the neural network. That's what it means. And problem space is the problem that a human, an engineer found.
And previously the unnormalized input.
Oh, yes, the normalized input vector, but yeah. Or you could have remembered the numbers that are not normalized. All right. Moving towards the ownership. Well, very similar stuff. We indexing into the values of x that we know stand for these particular entities and through the heading speed and through the speed. And we know that there are some numbers here.
Expected to be also use the universe to normalize somehow? I would have to write it myself, or that's the.
So, yeah, so you're absolutely right, is that vehicle needs to work out to normalize, and then when you go counterexample out and verify, you need to map it back into the domain. So vehicle will automatically try and calculate the inverse normalization function. We're kind of lucky in the sense that verifiers can only handle linear properties.
Oh, I see.
So
Yeah.
so you're kind of okay in that sense. I mean, in that you usually can compute it, and if it's undefined enough, then you can pull back into a Watson relation or something. In practice, I think people would love to verify linear specs, and if you over approximate, and then you have to over approximate in terms of the linear approximation of your non-linear spec, and obviously then you have completeness issues where you might generate a counterexample, but that doesn't actually fall within the spec. I think it's some interesting research on.
But we don't do that. I mean, when you do bugs, right? You do that when you do verification and bug finding. You do after interpretation, there was we have the problem and your safety and usually don't want.
Yeah.
To draw this picture, right?
You always do like a character or that.
Yeah.
So it's not like a new problem, like a new setting. Sorry.
Yeah, no, but there are many old problems arise here. Once you cast it in these terms, you suddenly say, oh, they're very standard, but until you do it, you actually, some of these problems just hang around somewhere under the hood. Yeah. Okay, and finally, the score of COC will not be minimal. Well, this is our friend for all, so surely I will ask you what is the range, what is the domain size here, so please have a look. But so for all indices, so minimal score I, if for all indices that are not equal to I, index at I is less than index at J. Okay, and then of course exercise for you. What kind of domain for all regions over finite to infinite?
When you'll think all of five, like this is
Yeah.
Yeah,
okay, fine. Yes. But you know, be vigilant because that will not always be the right answer. And well, now we're packaging this all finally into the property. We've done all the bits and pieces of this specification. So property 3 is now stated much nicer, in fact, than the SMT spec with which we started this little section. It's really readable. Okay, it hides all these ugly numbers, but the intent now of the engineer is very clearly visible. You see here a few Boolean functions and implications, so they're all part of vehicle and also not. Matthew will recap for you the language, maybe or not. Okay,
Maybe
but okay.
it's not very context.
Okay, a few questions for you. Can you guess the purpose of this at property syntax?
so you need to compile it down.
Yeah, so anytime you interact with something external, and vehicle is the vehicle for external communication, essentially. Yeah, so this one, are we importing or importing something from vehicle?
You're spotting.
We're shipping this property to this solver. And what kind of domain for all ranges solver? Is it finite or infinite? Why?
Like, yeah, there's the, I don't know if that's almost good. But like 5 vectors of all points.
Yeah.
But this is some problem.
Yeah, it's problem space, and but yeah, it's still an infinite number of vectors of rational numbers, even with those constraints that we've set on them.
Does it sugar into for each, or it works out if it's finite?
When it works out on the type of an instance resolution finds the implementation for that type, if it's a finite company.
For each.
Yeah. No, for each and then fold over for each, right? Because for each constructs event. right, for each of the vector. It is a map.
Oh,
It's
I
like-
see. Yeah,
So you need to fold it, it's for each, and then you wrap it in a big
sorry.
But we're done. So it was actually very, if we didn't have the discussion, the spec is literally 20 lines. We're done with the spec. So you need to have vehicle and Marabou installed because vehicle doesn't verify anything itself. You could get them in our tutorial repo. But once you have this one way or another, you have a vehicle verify command there in your terminal window. And you need to provide a few of these options there. So specification, you need to provide the VCL file, which we have just written together through the slides. You need to tell which verify it is. At the moment, it is only Marabou, but it exists here because Matthew and Gwen wanted to potentially extend to more verifiers. So in future, probably a choice here, but at the moment, not very much a choice. You need to provide the network itself, this function that we declared type for, but didn't really define in language. Oh, and this is an interesting one. Actually, from the example that I've shown you, it doesn't look like we really need it because we only defined properties 3. But in your file, you could define all 10 properties in a single specification and a single VCL file. And then you can actually direct which of them or maybe all of them you want to prove. So in this case, it just says look at into only that part of the file. And then it will give you something like this. So, well, the question to you, did we succeed or did we fail to prove that this property holds for this particular neural network? Yeah, it found the counterexample. So this particular neural, the result is this particular neural network is not safe. It will show you minimal real conflict even if it shouldn't. So it's a bad neural network.
And crucially, those values, as Oka pointed out, are in the real values in problem space, which no other system will show you. Like give you values.
I'm still a bit confused about some point. Like, where is something?
But it would be great if there were units on everything. I mean, so the first one is meters per second. The second and third ones are radians. The third one, I think, is sorry. The first one is meters.
Yes, you know what I mean?
Yeah. You're right.
I mean, it's a pretty problem.
Yeah, the first version should be.
So mine has a lot of memory. You know what I mean? Yeah.
Oh,
Out of memory.
Well, no, it's a detail, but it's the most common error is I don't know, it just says nobody only single form, I don't know what single form is.
okay, let's take
Let's
it
get-
exercise.
Yeah.
Yeah, but it used to be okay. And today I did this morning, but there was update of the system. This morning I didn't run this, but I ran other exercises and they were all fine. Martin.
We've all had tools before. We all said it, don't have to.
Let's demonstrate. So I was planning to do a little.
Yeah, do you want me to go through
was-
this?
I
You
was
want
gonna
to do it?
that's okay.
Okay. Yeah.
So yes.
Some kind of a reference environment where we can all of these definitions.
We don't have a REPL environment yet, I'm afraid. There's enough backends that we've really just been working full time on doing that. I'm afraid we don't. It's future work. One would really like to get it working on Jupyter notebooks. It's the current plan. But, yeah. Okay, so here we have the specification, and this is full.
Yeah, because
I can't see.
see, no, it's too much. Okay,
So how can we zoom in on this?
first zoom and then I think it looks in parts. Oh no, it doesn't. No.
So here we have the full specification, which we've written, and actually we have all the properties in this file: property 2, property 3, property 4. So just to demonstrate that it does at least run. So this is the command, and actually it's super quick. Let's just spit out the counterexample. So I guess the interesting thing is the limitations, right, of the verifiers, and how do we deal with that? Because we've given people a really super expressive higher order functional language, but the verifiers are really limited. They can only solve linear specifications and they can't handle alternating quantifiers. And so what happens when users write specifications that they can't, doesn't work? And it's super easy to do. We end up writing, even the team members end up, right, we call developers, end up accidentally writing nonlinear specifications. So it's really important to work out what vehicle actually does, work out a good way of providing feedback to the user. And that's, for example, let's try and make this specification non-linear. So in valid input, for example, where we said that for all xi is between minimum and maximum output values, let's make this x squared is less than, and what happens? Ooh, that's very small.
What happens at the bottom of the screen, and the most interesting thing is that
Yeah, sorry. Yep. Oh, yeah. Yep. Sorry. Yeah. Yep. Yeah. Oh no, it's gone again. What's the command shortcut for this? Okay. So what vehicle actually spits out is that it says, gives you the property 3 contains a nonlinear constraint which is not supported by the Manbury query format, and it actually gives you a trace of explaining exactly why the property is nonlinear, giving you line references for every function application where the variable x goes through. So it says the quantified variable x is introduced at line so-and-so, column so-and-so, and then it's used as an input to the function valid input that we just, and then which is used on the left-hand side of the multiplication and right-hand side of the multiplication. And this works through higher order functions. It works through, we have a similar error messages for alternating quantifiers. And I guess the reason why I'm highlighting this is because I would like to talk, it's how the vehicle compiler is actually designed. And in particular, it's how we use the type system, the type checker. And we have the standard pipeline. We go through scoping, we type check, we normalize, and then we compile to the queries. But what happens when we get an error is that we actually then re-invoke the type checker with a new set of types that does the linearity analysis. And this linearity analysis, I mean, really relies on all the features, the really powerful functional programming language features carry out this analysis automatically. So it relies on backtracking instance search, it relies on dependent types to compute operations over the provenance information in the types for this. So the features that we've implemented in the language, the powerful language features, are really weirdly not for the user. they're not used. We don't expect people to use dependent types in their spec, widely or right dependent types, data types, but we do need them in order to implement the backend analysis. And similarly, we have similar things when we get a quantifier error. And I guess the question is, why have we not just bundled this in the first type checking pass? Why have we got this modular retype checking in our compiler? And the answer is because it's we're going to get, as we're going onto it, it really is a multi-backend system. So when we want to training, we need to do an analysis pass that tells us what part of the specification should be differentiable and what part shouldn't be. So when to convert which bool, as Katia will explain in the next session, which bool types should really be converted to differentiable quantities and which should remain bool types. So our type checker, again, we have another type checking pass in the training backend. And actually, when we export to actor as well, we need to decide which Boolean predicates we need to lift to the type level to express the property in an interactive theorem prover. And that's again done by another type checking pass. So having a modular type checker with all these expressive features really aids the analysis in the back end. It's not for the user, weirdly enough.
So is your type system like linear, right?
So it is not, no. So when I say linear, I mean linear as in the algebraic sense, x squared, you know, cubic, in the arithmetic sense. Sorry, in the yeah. Yes. So it's not linear. No, there's no linear types.
Linear.
No, yeah, it's an overloaded term. Yes, yeah. Yeah. And this is, I think I've mentioned most of these. So we have modulars, complete generic, so building types, factoring instance search, automatic generalization over unsolved methods and instance constraints, and dependent types. Okay. Yeah. So do you want to take back over? Or I can keep going.
I'm not sure. There's very little
Yeah.
in this chapter, but yeah. So we have. Oh yeah, I will finish with one little thing. There is so we've just only covered one branch in this design, from property to the verifier, and I'll just finish with this question to you. In just this one example that we've seen, which of these properties we've covered?
We had the interpretability,
Yeah,
because we were using the problem
Yeah.
space.
yeah. Anything else? And the embedding up, we had a look at, because that's the source of errors. Yeah, so we've had a look only at two, and the other two will be covered in due course. Oh yeah, it's if you wanted a more interesting exercise, and this is explanation why we started with property 3. We first wrote property 1, and our early versions of the tutorial were starting with property 1. And it took us a long time to realize that actually there was hidden normalization on the output as well as the input. Yeah. And so, and now we have put this as an exercise, because if you understand the problem of embedding gap between problem and input space, this is an additional one, because it has a gap on the input and it has a gap on the output. So if you wanted to test your knowledge, you could try to formalize that in vehicle and use this normalizing function, which Matthew found somewhere very deep.
Very deep in some piece of Python that they use training.
Okay, but so this is like a star exercise for the exercise session if you wanted to, and this is the end of how are we doing? So it's 1 hour, and you wanted to show demo of robustness, I think.
3 minutes.
3 minutes.
Oh, 3 minutes.
Yeah. Well, we can quickly have a very quick look at the robustness spec, including a robustness.
What would you use it for?
No, break is now, right? Breaks in 3 minutes, right? Yeah. Okay.
Okay, Matt, you kind of answered, and then we'll come to this again at the start of the
Wow.
session.
Well, maybe we'll skip to yours. So we now have multi-dimensional tensors, because we're doing over. So we're going to do that MNIST handwritten digit recognition thing as a nice example, because everyone knows it. We have tensors in our language as well, not just vectors. So multi-dimensional tensors, although really it's just a wrapper of vectors. In the, at least in the functional part of the backend, we compile it to real tensors and TensorFlow. We have labels. We have what it means to be a bad image, that all the pixels are normalized between 0 and 1. We have again a new network, which is classifier, and we have what it means for the classifier to advise label the image X should be with label I, which is for any other label J. As long as I does not equal J, then the score for label I should be higher than label J. Okay, so the next thing is that we have this new keyword called parameter, right? Which is, if you remember back to the epsilon delta definition of robustness, that epsilon and delta were tunable. And you don't want to, ideally the user may want to vary that with different experiments, so you really don't want to have it hard-coded in the spec. So you can write the parameter keyword, and then you can pass this in at compile time with the value of epsilon. Not terribly interesting, but a small usability feature. So we can then say what it means for the image to be the new image, the perturbation to be no more than epsilon size. So for every pixel, the value of the perturbation x is between minus epsilon and epsilon. And then we can define what it means to be robust around. So we can say that if you have an image and we know that the true output label is the value label, then for every perturbation, we take the perturbed image. And if the perturbation is smaller than epsilon, and the perturbed image is still a valid image, then the neural network should advise the same label as the original image on the perturbed image. And okay, so this still isn't the problem, is that this still isn't the property, right? You still need to provide an image and a label that you are actually going to verify this over. And the answer, what people do is that they take their training data set, and they verify that all the image, it's robust around all the images in their training data set, typically. We can have a discussion about what that quantity is approximating, but so we really need to interface data sets with vehicle as well. We need to have data sets in the language. And again, we don't want to have to make users actually write out the images in the vehicle spec. So we have the data set keyword. So we can say there is a data set of training images and there's a data set of training labels. Crucially though, their sizes have to agree, right? I mean, you'd really hope it was the same number. We don't have product types in vehicle, and in fact, the way that data sets are stored are often not stored as on disk as separate. So we in the same records. So we have to have separate data sets now with their size agreeing, and we have inferable parameters n, which just says that there is some natural number n, and you should infer it from the use in the file what the value of n actually is at compile time. So you don't have to pass it. It's determined at compile time, but you don't have to pass the value explicitly. And then we can say that the network is robust with respect to the training data set if for every image in the training data set you're robust around the image of the training label. And you'll notice that this is no longer bool. This is a vector of booleans, this property. So it will actually give you it will verify each one, and it will give you statistics about how many, it'll tell you the result for each one, but then give you statistics as well. And then I guess if we run this, thinking. So this is a data set with 2 images, so it's verifying the first image, and to verify the image, there's 9 queries to the verifier that we compile it down to. It's not a single query, it's many queries. So it goes away and runs the verification. Yeah.
This is checking that for every ball smaller than 0.005, it's smooth on that ball.
So yeah, so it's saying that if you allow any pixel value, all the pixel values to vary by at most 0.05, then it still gives the same answer. And hopefully it's going to say it's robust around the first one any second. Yeah, and it says prove no counterexample process. And yeah, again, you pass these all the external resources you declare in the specification in. So these are the actual. I mean, this is actually the object this is actually the neural network that's used.
It's parallelized, but it's sequential.
It's not parallelized at the moment. It is running on sequentially. Marabou itself is parallelized, so but obviously not all verifiers are. So there's probably some work there that we can throw out. To, yeah.
And the group is completely separate from each other, or so you reuse it like.
So it would be.
There's something next one.
So no, so they are completely disjoint in this case.
You know, if using one as the assumption for the next one will make it faster, or we haven't tried that.
So
you
what
applications?
Yeah.
Once you establish probability 1,
yeah,
probability 2, you can say probability 1 holds. Here there's some probability.
Yes. Yeah, so
that's speeded up or as not.
It very much depends on the structure of your property, I think. and whether it provides useful information.
Syntactically, whether the structure of the property is appropriate and then use it.
You could do, yeah, that's a very good idea. I mean, the thing that really would be would be good is that actually if Marabou internally reused the constraints that it had found between queries, exactly. But that's the thing that would actually improve performance. That's a real thing that I think would improve
But
performance.
then you really have to open up the box to verifier and
Yeah.
look at how any problem with the SMP solver.
Yes.
Bypass them. So it's
Well, not bypassing, but if Marabou just had support for loading in, it produced artifacts between queries and you wanted to run multiple queries on the same neural network and then it could load in the previous
So
thing.
here's my problem. I'm grabbing you. Here, this is good. And
Anyway,
easiest to talk to the office opposed to those guys.
Yeah.
So let's move this about, but it's like flat, it's fine, whatever. But in general, right, like we care about this being some like basically like robustness function of continuity, right? But like we
Yeah.
would also care about the neural network changing the application of your code. And
so the output changing very
like
Quick-
quickly, but finitely, right? Like,
okay, but this does capture that as well, right? Because you as in you don't want to change it quickly, or you do want it to
well,
change?
you don't want to change it.
No. So there's various different definitions. There's Lipschitz continuity that you can
Sure, yeah.
right, or there's yeah, but it depends on. But the nice thing is that vehicle really gives you control over. I mean, a lot of the verify frameworks hard code in a particular notion of robustness, and then you go away and you try to solve that notion of robustness. Vehicle really will. You can really write exactly what the definition of robustness wants to be, and it'll go away and check it. Okay, we should break for coffee. Cool. And yeah.
It's helpful to train to help us.
Oh, cool.
Yeah, but not successful.
Okay, so, you have any problem?
Well, it's not a memory problem. With valid on my test in my office, like it can be written.
Has she found?
She was on the list.
Uh,
If I knew what to like, maybe it's maybe my Marabou.
So it is.
I know what to call Marabou. Can I extract out what this sends to Marabou?
Yes. So if you put -- logging,
Make detail or mid detail.
We have finally speaking on my minutes to
I'm not sure we were actually translating it to anywhere. I don't think we're on YouTube for it.
Yeah.
I would have done it.
That's logging.
The
Capital. Sorry, capital and detail.
It's a big coffee here.
no, it doesn't help.
Anyway,
Okay. Well, the command is if you change the verify command to compile. Sorry. Verify then file between that to compile and that's the American queries. This are paste. Yeah. And then go -- capital. Sorry.
it's not good target anyway.
Yeah. And then if you go down, then you need to go, so that's the Marabou breaks generated.
Okay.
So if you go grid, and then you go, full Marabou, and then you want to pull up and then net work. So, on this slide, which is cool, I think that's it. And the query policy.
Leaving instruction. No, it's just program.
What?
This is the name. So it's not that she's having this stuff working. It's very
Yeah, so the problem is that you are very mindful of the verifiers being.
Yep.
Sometimes they let you down. So what operating system are you guys on?
Ubuntu Linux
That's
native.
That run Python. So I got the log file here
Yeah,
and.
Yeah.
This usually run everything going to map.
yeah, so we just found it's Marabou is killing itself or something.
I don't know. It's in the.
It's weird that you both have the same error. I've
I
never
think
seen that error before.
I think it's probably because we just downloaded the new version of Marvel. We upload your version.
Are you going to be here?
Or next, we're gonna say it's fine.
I'm very reluctant to try that actually.
We fix the edges of the projector.
Okay.
So there's come here and
Well, let's just download.
I told them it's size before them.
Yeah.
Should take it.
Check.
I'll go in the other room and check it.
Right, thank
Last 2 weeks.
I think the screen was fine otherwise.
Yeah, everything works.
Yeah, that will be really nice.
So I know everything works, but then just wait by.
I'm not coming back after the break. I'm going to all the sessions, but
thank you for
but
coming.
no, it was good. Once you like, so if you need more, information about Ask Me, once you divide it, then place it more. So it's we've got people now. Because I can't do my office, I can do it.
Yeah.
But it looks like I looked at the online, it's comprehensive. A really good like high level view of this. And that's great. Thank you.
Okay.
We were going today, we broke 3 minutes, we broke at 33 past, right? And we went up at 34 past and all the pastries.
Yes, I know. I'm not sure if he wants to do it to
That's okay. 3 wasn't too bad.
I don't think you will write the machine, but, well, I attended a good conference. There was some result there. I think that if not this competition, if, I'm not saying tutorials could be, by the way, time when I attended. I have a feeling that tutorials which is given away without the option. You didn't have to choose very important topic. And now it's not just 1 or 2 for. Why invite people for asking? And if it's not that, probably would. It couldn't be like mainstream interest by CP community, but we would have time. It's my. That's what I'm saying, so, why do this, it's fine, not really meeting them. I don't know, but I mean, you say go to big AI conference and then they run it and then it doesn't run.
Yes, but
It's very fragile, I mean, but to take points, part it's not equal, it's vulnerable, but it has still doesn't cancel the problem that it's very fragile. Therefore, remember, oh, did you attend my classes, when we invited him, remember, we paid him a large sum of money to engage with the capabilities. And he gave this, SPLB tutorial, and we said, oh, come on and give a tutorial session, etc. He said, no. Just, there will be no practical session, and I said, you know, because I still need to school, we do encourage you to have exercise sessions. He said, just, no. There's no way you can persuade him to have a practical session. And I think this is because of this, right? He knows very well that, when people actually start running and they will immediately, something doesn't run, and then he will run around debugging, and this just doesn't show Marabou in the best light. So, yeah, I think they see Marabou to be a technology, right? We don't see it, but they don't see it as like tool for the masses. They still think there will be a very right people who, if someone needs, will be able to define your ecosystem, but it won't be like every person.
yeah,
But I remember I was surprised when guy was he was just categorical on tutorial sessions, but why? I mean, this is a nice little, I know.
well, maybe the answer is to do ensemble methods. If we add support for another tool to verify, then one of the verifiers will run on something.
Yeah, so it's slightly
It
different.
looks like the projector's off a little bit, but it looks like the screen's fine.
If you can reduce the size of it, because you see the right hand side is just getting out of the.
Yeah, it's getting out of focus. I just need to readjust the projector itself.
So you can just adjust the projector, and I think the screenshot is pretty good.
I think the most interesting part.
Blow that
Okay,
up.
so we're not gonna be.
And we're going to lower it a little bit. If I need to raise it back up, that's fine. But for now, what we're going to do is we're going to, no, not that, stop that. I'm telling you, right? If only if our lives didn't depend on it. Which laptop is this projecting off of right now? On the podium? Do you mind if I
Absolutely, feel free to.
thank you. I'm just going to. Now, what I want to do is try to bring up I just want a blank screen to bring up like a white screen if we can. That way I can see right in my face. Thanks. Sorry. I was working on it. I know. I was just having trouble seeing with the black. So yeah, there we go. Perfect. If we can just get, yeah, that'll work just fine. That'll give us a little bit easier time to, you know, it's a shortcut on if you, like hit exit, if you just hit that button once, it'll actually give you the thing, and then there's 4-corner correction right there.
And I would also get that thing out of the way.
And then you have to hit the enter button. Yeah. And then it'll pick the corners for you, which is kind of annoying. Yeah, it is. But I got Olympic taken care of.
Yeah, I saw that. I put that in the chat.
Were you monitoring your chat? You might get questions here if you have audience, but I don't think so.
I adjusted the optical zoom on it to give it a blown up picture. So if we need to shrink it back down. Now,
Okay, there you go. I think this is
lowered it
much
a little
better.
Too much, but I wanted to make it sure so we can fit it to the screen. You were saying something about Orcus?
Yes.
Do we need to go take a look? If you guys got this, I'll follow
I
him
need
to.
to retrieve a webcam, so I'm not sure if the room is open.
Oh, okay, yeah, I can do that.
We are not using this.
Okay.
Easy, that.
Okay, that's right.
It's not the most intuitive thing. It's
I
definitely
mean, it's
better
an
than-
order, like you can't mistake
Yeah,
which one you have or have not done in theory, but it's not. It's just better that it should do it flexibly, just pick your corner.
yeah, like the short ones.
Okay,
Okay, thank you so much.
of course.
Definitely when it's exception, we can try to pick up this one to your Bluetooth. Unfortunately, can't hook it up to this one because it doesn't have Bluetooth. So if yours has Bluetooth and you want, we can use this speaker. If not, it's a small crowd, so we can as well
Yeah.
use your laptop speakers.
Yeah. Host has approved. So Wen says that she's tried to join the
Yeah,
Zoom.
no, so there, we needed to click here,
Yeah.
this is the host laptop.
Yeah.
Um,
Okay. Great. Let's try Bluetooth. Right, let's finish. Bluetooth on. Bluetooth settings.
This some kind of this. Yes. Something just.
Phone melodic. What's it called?
Flip
Five.
Yeah.
Flip five.
Good.
Cool.
You have interested.
That's an important thing, by default, we will just say.
There was nothing, but.
Mhm.
You also have program scientific computing. That will be a lot of the machine learning.
Because they were not.
I can't bring the Zoom chat back. Oh, there we go. Hey, Wen. Hey, Wen. Can you hear us? Would you like to try talking? Okay, so I'm just going to bring up the side deck. Really. Oh, no, virtual business.
One question regarding the language design.
Yep.
It looks like the syntax is very similar to Haskell.
Yeah.
But then you have a Python decorator going in.
Yeah.
So what it is like. Is that something that you wanted from the beginning or something that you added on later on?
The decorator specifically, or so originally we had keywords like type or network, but the problem is that sometimes I mean we had an issue where we wanted to add multiple annotations to something and they didn't work as keywords terribly well. And we thought that Python people would be happier with, I mean, the decorators, decorators are kind of known in Python. And we thought people might be a little bit more happy with that syntax. And as you can see, we can provide keywords to the parameter when we have inferable parameters and stuff. So it's slightly more flexible than having keywords.
We should start with a YouTube.
Oh yeah.
This it is an impact, so maybe we'll start.
Yeah. Okay. Cool. So if you want.
Okay, so yeah, we'll go now for training because that was one of the branches that we wanted to implement from the very start. So in this section, we will discuss why and how training is part of verification of neural networks, what choices exist for implementing this generally, and what choices VCL specifically makes in this respect. And also we will touch upon theoretical and practical issues with the chosen methods and VCL's take on them. So we have been going through these 4 PL problems and we were saying which ones we were solving. And training obviously solves this very first problem. You want the single property to be portable between training, counterexample, and verification. And this is what we're going to be looking at in the next 30 minutes. So why training is part of verification in the first place? So this is something that we have seen in the previous section. We have a neural network, we have property, then we ship it, and then it's not verified. So this is obviously not a satisfactory result for an engineer. He will say, well, do something about it. I must deploy the network. So you have to go back and make sure that you have a network that satisfies this property. Either you train this one or generate the other one in some way is a choice, but it's usually not a choice to just have this result theoretically reported. Everyone wants to actually run neural networks. Matthew has shown you the run of verifying MNIST in the previous section, and I think he used for epsilon 0.005. At one of the exercises in the tutorial page, which you're invited to go to, says, well, could you try running the same experiment, same command line, and put different values of epsilon in the command line? And this shows the result of one of these experiments. One of our MSc students, Ben Koch, was using VCL for his MSc dissertation. This is one of his contributions to the tutorial pages. You can also find this on the tutorial repository. But basically, he has taken, you have seen MNIST, but he has taken a different data set, Fashion MNIST, and 500 samples and ran the statistics over 500 samples. So for epsilon 001, about 413 of his epsilon balls that he was trying to verify were actually verified, but some were not. But as he started to increase the epsilon, very soon you come to the situation when nothing is verified. And in particular, at 0.5, he reached that point when he couldn't verify anything any longer. None of the epsilon balls around his chosen samples were verifiable.
We should say that that's a good one, because the 0.5 means that every pixel can change the value by 50%. So you can change basically any image on 0.5. So that is what we'd expect. But at 0.05, every pixel value can change by 5%. Maybe at that point, we really would like to have 100% verification rate, because you really just and definitely a 0.01, 1% change of the pixel. It's very good. The image is definitely recognized. Really would like to.
Yeah. So and this also partly depends on what kind of distance you use, but for some distances you would, yeah, in this particular case, because it's L infinity norm, 0.5 is half the pixels, but in some cases, 0.5 would actually be a more sensible value. But anyway, the game changer in this domain is you want to enlarge epsilon balls as much as you can while also being able to verify them. So in the previous example with ACOS2, we just couldn't use the neural network at all. And even in this situation, you may be asked to increase these values somewhat. And someone may ask you, could you please go and retrain and make sure that here we have 100%, or I don't know, make this 29 and 8 in the 50. So this is very common scenario in machine learning, to try to retrain the neural network so that it can verify more. And if it's so common for machine learning community, then the question is, well, maybe machine learning community has already solved the problem. And indeed, if we look at the literature in machine learning community, we will see that actually the literature that goes about retraining neural networks with certain property in mind has come much earlier than verification papers in that same domain. So 2013 was the seminal paper of Szegedi and others, finding that even neural networks that are very accurate and generally perform very well are susceptible to what's now called adversarial attacks when you change just one image and the whole classification changes. And between now and then and now, there are tens of thousands of papers on this retraining of neural networks so that you could improve your statistics of robust epsilon balls in your data set. And in terms of verification, and this is the Marabou tool that we were using in the first session, it actually came, well, not so much later, but 4 years later after that work. It was, of course, informed by the work in the machine learning community, but it came much later. And it's not tens of thousands of papers since 2017, but hundreds of papers on neural net verification. So it's much smaller community. I'm showing this because you could think, well, because this is such a huge body of work, surely we'll be able to just grab some nice method out of there, plug this in the vehicle and job done. And let's try. And this is exactly what we tried. We wanted to use any out-of-the-box method from machine learning community, and we did not initially set up to do machine learning research per se. Well, if you think about this logically, training of a neural network depends on your data, depends on loss functions that are responsible for the gradient descent, and maybe it's also changing some other parameters like shape of the functions. And let's start with data augmentation. Since we can improve data, then of course you can improve data in a way that is benefiting your property satisfaction. So suppose we're given a data set of some n data points. Think of them as images, if you like, if it's image data set, but generally any vectors, so x1, xn are vectors of rational numbers, so real numbers. Then prior to training, we generate new training data samples close to existing data and label them with the same class as the original data. So if we look at this picture, we have input space, we have data manifold, and we have some examples from that manifold, right? So they're all lying on the manifold. So this x1, xn, you should think all these x's are those input points. And the circles you see are the epsilon balls around them. So we essentially draw these epsilon balls around every given point. We sample them and then we add them back to the data set. So there will be a few points here added to the data set. So we enlarge the data set with new samples, but crucially, whenever we sample from each of the epsilon balls, we give them the same label as their parent, so to say, as the center of the epsilon ball. Okay, so this seems like a good idea. So why not? But there's a problem with it. And here's the problem. So depending where the decision boundary lies in your data manifold, this method may or may not be such a good idea after all. So if that was your decision boundary, and by decision boundary, we mean it's desirable decision boundary for a human, this is where decision boundary between one image and another image class in one class, another class lies. So if that's the decision boundary, and we start sampling blindly, right? And the method with data augmentation doesn't know anything about the classification boundary, and gender classification boundary is not known in advance. And we already started to sample, and we assign same class to any sample on in any side of this epsilon ball. Then obviously we're not really directing neural network according to the decision boundary it should respect. So, and this is the cases when we see that data augmentation harms accuracy, because you essentially generate misleading examples in your data set. But it can be worse than that. Your epsilon balls, theoretically at least, can also intersect. And then if you sampled from one and you sampled from another in the industrial area, then you simply give contradicting labels to the same data set. And obviously, since we're trying to increase our successes of verification, if for machine learning community, maybe it's not that harmful because statistics will swallow any inaccuracies, but for us, it's not very elegant solution because we're essentially giving inconsistent labels. So we didn't want to live with this solution for this reason.
Briefly, this also only works for the buses.
Yeah, I'm coming to that. And so then what do we want then? Well, we want to be able to say that we, instead of just assigning firmly a label to data, we want this assignment to somehow depend on how close the points are to the decision boundary. So points in this case should be stronger in the yellow class, and points here should be given with less certainty. But of course, if you generate a data set, there is no way to annotate a data set with probabilities. So there should be some other way rather than data augmentation. And surely enough, machine learning community found out a way to give this softer kind of information, softer constraints through training. So we need to forget about data augmentation now and go into the adversarial training, where we're going to give approximately the same information, but through influencing the loss functions and the training itself. So this is how it goes. First, we need to recap what the loss function is, given a data set and your neural network, which is a function from vectors of reals of size n to the vector of size m. And here, before we were just saying f in the previous section, and now we want to say theta here because now it's very important for us that there is some optimization parameter hidden inside of this function. So we're thinking these optimization parameters there. We define a loss function to have this type from Rn and Rm to R. So it essentially computes a penalty, just one number, proportionate to the difference between the output of our neural network on the training input and the desired output y. So if these two deviate a lot, it will be a large number. If they don't deviate at all, it potentially could even be 0. So an example, so this is one of the classical examples from machine learning, cross-entropy loss function. In this case, it assumes that your output will be vectors of reals in the interval 0, 1. And well, let's just have a look, and let's just try to match our general definition of a loss function to a concrete one. So it has two inputs. One is of type Rn, the other Rm, and well, here you have a sum of y times log of theta xi, where this is used in notation for probability for class I as predicted by x. But this is mainly an example to show that our general definition matches the standard ones from the literature. Okay, so what does actually adversarial training does with these loss functions? So the standard algorithm that's used in machine learning community is gradient descent, and it minimizes the loss between the predicted value theta x and the true value y for each entry xy. So this is a standard. This is before we bring in the adversarial problem. It's normal to theoretically say, well, gradient descent as an algorithm solves the optimization problem, and we use notation like this. So there is the loss function as defined previously, and we say, but what we want to do is we minimize this loss, and we minimize this by optimizing theta. So this is mainly a notation on top of the concrete gradient descent algorithm that works there. For adversarial training, you want to change this optimization problem to something slightly different. So we want to minimize the loss with respect to the worst case perturbation per sample. So if we wanted to use this notation, it would translate into these terms. So we're minimizing the loss that's inside of these square brackets, and here we're maximizing the X within the epsilon ball. So there's this min-max maximization minimization problem. So the inner maximization is done by what's called projected gradient descent that looks at the gradients of your neural network and then tries to use them to compute the worst X that is the perturbation. Is everyone okay with this notation? Okay. Because we're gonna use it very soon, and not in a very sophisticated way, but we're trying to draw from this example because we'll clearly need something like that in vehicle. And then there are more and more ways to do different optimizations. There is Lipschitz continuity, something we'll not go into this tutorial too much. So we have just seen two ways to influence training by changing data, changing loss functions, and just to say there are more sophisticated ways to influence training as well, by tailoring neural network architecture, activation functions. There's a survey here, but I will not go in there. So we will just focus on loss functions for now. Point being, the hope is great machine learning community knows how to make neural networks robust, and maybe then there will be more neural networks even verifiable if they are more robust. But remember, because we are not just interested to make neural networks more robust, we're interested about our philosophy points, and well, interoperability and interpretability are important for us. And let's have a look whether we actually can get these just by taking out of the box, out of the shelf adversarial training. Well, first thing that we noticed is that there was such a choice of robustness definitions in the literature. And generally speaking, if you look at any robustness definition, it will generally have this shape. Where the X in the epsilon ball of my X hat, this B just denotes an epsilon ball for a given X hat. I want to prove that the output of my neural network for any of these inputs is robust. So this scheme is more or less there everywhere in the literature. But what's not there is not uniform there in the literature is the definition of this robust. So the epsilon ball is pretty much standard, but robustness not. And when we actually looked deeper into this problem, it turned out that different training style that we could find in the machine learning community optimized for slightly different robustness. For example, it happened that for data augmentation, the property that you're actually improving would amount to this definition of robustness when you take the output of the neural network, find the maximal element, and this should be I. And we call this classification robustness. There are other papers that we found that were optimizing for a similar property, but instead of saying the maximum output or the maximum output element is this, it was saying, well, maybe it should be greater than some given eta. The adversarial training we've just seen corresponds to this property, which Matthew introduced in the morning session, and we call it standard robustness. The Lipschitz continuity methods correspond to something slightly different when instead of just comparing outputs and saying it's less than delta, you also introduce constant L and compare that there. Compare how much X and X hat deviates and how much of F and FX hat deviates. Anyway, there are many options there. And it seems like if you just go there blindly, pick up any method from machine learning community and plug it in, you're actually in danger of optimizing not for the same property that you're trying to verify. So that's not very good. That's actually, there are more bad news about this. One kind of robustness doesn't necessarily imply another. Yeah, and optimizing for one kind while you're actually verifying for the other is not a very good thing. And actually, the second problem arises very often in verification community. In majority of machine learning and verification papers, adversarial robustness is used, and so it encourages standard robustness, but verification is done for classification robustness, which is not very good. So we didn't want to replicate that. And finally, the third problem is the one that Matthew mentioned 10 minutes ago, that even if you somehow brush this off, there still will be a question and what to do with properties that are not epsilon-bound robustness, because our language is very general. It's not just about proving robustness. And then none of these previous machine learning papers applied to more sophisticated properties. So we tried to use standard machine learning, but we couldn't. What we really wanted is to find some kind of scheme which would allow us to have the specification, to have the verifier and the neural network, and somehow verify and retrain for the same property, which would give us interoperability, and hopefully we'll have interoperable syntax as well, just inherited by VCO. So in VCO terms, we were looking to establish these connections from property into training, and perhaps counterexample search, because if you remember my introduction of adversarial training, it kind of already included some kind of rudimentary counterexample search by projected gradient descent. So VCO's formula is simple. We want to use the projected gradient descent optimization just as I introduced to you, because it seemed like a good idea. It gave us this gradual approach to improvement within the neural network. But we also want to use differentiable logic, and this one is needed in order to deal with arbitrary properties in the language. So let's start with the differentiable logic. I will give explanation of it by example. You can define in any logical language, but in this case, I'm defining a toy language. It has conjunction, implication, and it also has comparison between values. And then we could find a few differentiable logics in the literature, and this is one of those in the literature. But the idea is, for anyone who could find, the idea is to take the syntax in your logical language and translate it into the language of loss functions. So the easiest case in this case is this. So let's take conjunction. If I have conjunction in my language, I want to translate it to multiplication when I formulate it as a loss function. For implication is slightly more complicated, and there is some formula. Mainly the formula is so long because for this particular logic, we want to map it to the domain between 0 and 1. And this max here is as well. This has to do with the fact that you map all values in the domain 0, 1. But there are more choices. There could be more domains and other definitions. But the basic idea is that you recursively, for any expression written in this language, you recursively apply your translation function, and then you get the loss function out of it, which you could directly plug in into training. Well, for example, this is the second half of the robustness definition that Matthew was using in the morning. For example, this would just translate into this function. Many different differentiable logics exist. Fuzzy logic, signal temporal logic, DL2. I think, well, so one takeaway message, there were many. And my student, Natalia, is tried to summarize them all in one paper and also give them some kind of more general high-order logic interpretation for all of them. So if you're interested in differentiable logics, I would maybe start with Natalia's paper that also service the other choices that other people made. We will not go into this in this tutorial, but the choice of these differentiable logics does influence the properties of loss functions. So the one that I've shown you, this product logic, for example, it's smooth and differentiable, but some others no. On the other hand, then you can formulate some logical properties of those loss functions, and you may well have very good geometric properties of continuity and smoothness, but perhaps lack some of the logical properties. So in Natalia's paper, you could check that. But the point is, there's a choice, and actually there are consequences of the choice you make. In VCOL, we simply take all of them and allow the user to work with any, because we didn't really make a choice as to which one is the best. We left it for future generations of students to have a look at that. So, but the important part of the picture is that we have differentiable logic, or maybe several there in the compiler level. And how about then PGD optimization? How do we weave this together? So recall that with projected gradient descent, we minimize the loss with respect to the worst case perturbation for each sample. So we replace the standard training objective with this formula. So this is what machine learning community does as part of the adversarial training anyway. Well, what do you think is missing actually? So this, well, I'll start with one. So this was cross entropy usually, or any standard loss function. So we clearly want this to somehow reflect our logical property for starters. And then something else is also restricted in this optimization objective. Yeah. So it explicitly refers to the epsilon ball robustness, and we have no idea whether our property will be that or something else. So that's the two things that we want to generalize: how we sample, how we get this worst, the kind of worst perturbation, and also with respect to which property we sample. And this is exactly what we do. So really, it's a very mild adaptation to the standard adversarial training. So in VCOL, given a property, which we would assume has this general shape, for all x, px implies sx, we replace this training objective with the following. So we still want to minimize loss, of course, and we still want to get the worst perturbation, therefore there's this max problem. So this remains. However, instead of explicitly referring to the epsilon ball, I'm now forming a shape that corresponds to my property P. So, and usually, as we have seen in all the examples, for example, in ACOS-XU, through this collaboration with some engineers, I know the boundaries of this hyper shape, and I'm just defining this concretely, depending on the problem at hand, depending what this property is. But this usually defines some shape of inputs. And instead of general cross entropy, I want to get the loss function, which I generate using one of the differentiable logics from the second form here from the post-condition assets. But other than that, I really want to do the same stuff that those people do with modular generalizing this to reflect my property. Let's have a look how this boils down to the examples. So this is something that will verify. In this case, I need to define my hyper shape where I will be looking for the worst perturbation. And this is essentially given by the engineer already, except for this undergoes normalization and gives me my shape. Recall that for ACOS-XU, these were forming parts of the inputs vector. And for my loss function, I simply take translation through some of the existing DLs of this formula, not minimal scope clear of conflict, and then I'm able to massage the logical formula into a loss function. Okay. This is a degenerate case when we don't have any precondition, it's just for all x as x. Well, what happens then? If that is the case, I still can, of course, use my differentiable logic and get the loss function out. But in this case, my hypershape will just correspond to the whole of the input. So I'm a sample anywhere in the input. I'm trying to get the worst perturbation there. So my HPX, because I don't have P, just amounts to HX, something the whole of the input space. Because essentially, what I get here is that the input space is not constrained in any way. And how about robustness? So this is the definition of robustness Matthew was using. And so in this case, this PX, of course, then goes back to the epsilon ball, or perhaps epsilon cube, depending how you define. And the loss function is generated for the second half of the implication. And we've had a look over to this particular definition, this particular translation. Okay, so, and this is really all that we need to know about this part of vehicle. So it crucially uses the same specification, the VCL file, as you've written for verification. So you write your specification once. You need a TensorFlow version of the network you wish to train. So you have to have that somewhere available for vehicle. Using provided Python template, you call the specification network when running the Python script. And so the loss function will be automatically generated from your spec. And at the moment, we manually provide hypershapes, but in the future, maybe the work will be to synthesize this definition for hypershape as well. And then PGD finds counterexample within the shape that we defined. And usually native stochastic gradient descent training is used to minimize the loss function LSX. But basically, this is very much standard machine learning approach. Modular us changing the loss function and the hypershape from which we sample. And all of this serves to solve the optimization problem that we discussed. So this describes this part of vehicle when we compile down from the properties to the loss function and use it for training. And this, by the way, it is defined as this counterexample search by projected gradient descent. So this is not directly given to the user of vehicle, but it's kind of part of the training cycle. So we still have interpretability because we still have the same nice, easy code. And we hopefully now also have interoperability because same property is used for training and verification. So this is part of the training section. I'll give the stage to Matthew to talk about integration with Agda. And I suggest we'll take any question or discussion that we might have about training now.
So the big idea, the broader idea is you start with a network that's trained on like a loss function that's completely robust, that's naive, or correct, it's naive, and then you by these counterexamples, and you train against this robustness.
Yeah.
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 Do you sort of have any? Do you see any worries about performance on sort of the sort of naive set, when you do this sort of training on the initial training?
In what sense?
And
training points.
Yeah, how well the model does.
Oh, accuracy.
Yeah,
I think there's accuracy.
Yeah, sorry, the MLP folks call this performance, so it's easy to.
But performance, is it more, you mean more robust or just more accurate as
so,
the standards?
Yeah, on the, right, so the test set's gonna have some accuracy.
Yeah. You want?
Yeah, sure.
Okay.
I mean, what typically you do is that you combine the two loss functions together. So you take the standard data loss function on the data, present to loss, and you calculate that, and then you just add it to the result output by the loss function of the vehicle. You're actually training them both simultaneously. The literature shows we haven't run extensive evaluations with the vehicle implementation, but the literature that shows another differential loss function is that the accuracy decreases a tiny bit. That would, maybe percentage point or something.
Percentage point is huge.
It depends. I mean, so depending on training method, the data augmentation, it drops a lot. I think the loss function approach is slightly more, is slightly better and it does the accuracy better. I mean, it's not perfect, but the advantage at the end is that you're much more likely to satisfy it's a trade-off. And obviously you can wait which one you want to train. What you want to put more so probably more emphasis in doing.
But yeah, there was this paper there on the top that has a quite exhaustive evaluation what happens with and actually our own work. Remember when I was talking that when we discovered that different training techniques evaluate differently and come up. So when we started to study this, we also had a little bit of an evaluation what happens because, well, actually we didn't have exactly that question, how much it helps. But more we were saying, okay, if you optimize for one, what happens with verification for another? Because we wanted both empirically and theoretically show that some of the robustness definitions relate and some completely orthogonal. And so in this paper as well, we have a little bit of variation, but more along the lines that please do not do this, do not optimize for one and verify the other, because it either harms or doesn't help. You really have to optimize and verify the same property. But yeah, so there was a little bit of relation there and a lot more towards like the general question, does it help to train with differentiable logics? So it's more in that paper. So we took that paper as an inspiration when we decided to implement this in vehicle. We thought, well, it does look like it works.
Question, I think one slide you mentioned that when you see fashion implements the data.
Oh, you just got the experiments.
Okay. I'm just trying to, experiment with the other data sets, the training.
So the answer is that the Python integrator, the loss function integration, the most recent backend that we've added, and we're still adding out bugs in. We have plans to do thorough evaluation. So no, the answer is that we haven't done a big evaluation. We've really been trying to. I mean, the techniques in the literature are much more restrictive languages than vehicle. So our focus has really been trying to actually extend the differential logic techniques to a higher order function of the language with R 2.5 and stuff. And we're just reaching a new word definition. So we then can probably have students to evaluate with these questions.
I'm just curious about like weather data, for example. Sorry, so weather data.
Yeah, well, it in principle should work with any data, but we have a user who has, a collaborator who has security data sets and wants to apply this in security. We've just started basically, the way it goes is some tuning is usually needed when people come with the new application domain.
And I guess I can just show you the while we're here. Yep.
That picture paper looks like it actually helps the accuracy on a lot of models.
Sometimes, yeah, they almost, yeah, that's how we, it all depends on the loss function. Some of them are very good, but I guess the big lesson is you can't do it blindly. You have to know what you're doing.
Interesting. That helps. I guess you're putting the property of the problem domain it actually has the robustness property. It's like something that is true.
Yeah. Well, that's the thing, right? It should be true. I mean, the hypothesis, the function in nature that is actually operating, right? You're really hoping it does have that property, right? I mean, you know it has that property. So by giving that extra information, yeah. But yes, and we think that some of the problems in some of the accuracy drops are exactly because you're training for the wrong, you're training not quite for what you want. And when you have it expressed in logic, as opposed to just writing down the loss function manually, you can suddenly see that your logical definitions don't actually match up with what you're optimizing for. Yeah, just to give a quick indication of a vehicle interface. So this is Python code now. We just have a simple call to load loss function in the Python spec. You pass in the path to the specification, the property name that you want to pass, the type of differentiable logic you want to use. This is just information for the domain. At the moment, you have to pass in the domain information manually. Vehicle doesn't extract it from the spec. It should do. And then what it generates is this loss function. And you can just call this with your parameters. So the class, this is from a robustness spec we saw earlier. So these names are actually just taken from the spec. So these are the names that you wrote in the spec. You pass the values for the classifier, which is your model and your epsilon and your training images and your training labels. And it just calculates the loss value. And then you can wrap this inside the training loop with the automatic differentiation with the gradient tape in TensorFlow. And then you can calculate the gradients with respect to its loss, just as you would any other function. So that is literally, I mean, that's literally the vehicle specific code that you need to add to your training file. And then you just evaluate the functions that you're training with. So it's really lightweight integration, and you can use it as you please. So you have a lot of control over. Cool. Okay. So I guess what we're going to talk about now is the very final part of that diagram that we showed, which is the integration with ITP. So what happens when you suppose you've trained on your network, you've managed to verify it, and what can you do afterwards? And is that the conclusions? Or yeah, okay. So imagine. So yeah. Where did my sides? I didn't have a picture for this. Where did it go? Okay, gonna quickly. Maybe it's on my tutorial page. Yep, that's it. Yep. Okay. So imagine we have the following example. So we have a car driving along the road. It's an autonomous car. You have a crosswind that's blowing, very strong crosswind that's blowing up and down. So maybe it's a toy car, so it's affected by the wind. That's variable. There's obstacles you have to avoid on the road, and you have noisy sensor readings of where you are. So there's some amount of noise, you don't know, the colors know exactly where it is. But I mean, the end goal of this system, right, is to stay on the road. And maybe you get points for avoiding the obstacles, but the safety property that we really want is that you do not leave the road. And obviously this is a temporal property, right? This is for all sequence of bad sequence of observations, then for no, at the end of the sequence of observations, it will always stay on the road. And we would like to implement this as a neural network controller for controlling the car, and we'd like to verify that it actually holds. So for the first step, we can formalize this system in an ITP. So if we go into examples, so let's try and I really wish tools had consistent zoom functions. Can anyone remember what it is for Emacs? Control. Oh, that's probably when saying that. No. Because we haven't generated the file yet. Okay. So, how do you zoom in on this? Control X plus plus. Thank you. Fantastic. Okay. So this is an actor formalization of a model. So we have some state from the system. We have current wind speed, position, velocity, current sensor. We have observations. So this is instantaneous changes in the system. So we have the wind shift happens per time, and we have a sensor error that's at a particular point in time. We have the initial state, and we have some sort of controller. And and then we can have the next state function. So the time at the next state is the wind speed plus whatever the wind shift we observed was, and the new position is the old position plus your velocity plus your new wind speed. New sensor reading is your new position plus whatever your sensor error is at that particular time. And the new velocity is the previous velocity plus whatever your controller has output. So really simple model, but just to for example. And then the final state, given a list of observations, you repeat the final state by just iterating the next state from the initial state. And we can then define exactly what it means for it to be correct. We formalize the notion of it being on the road. The position, current position is less than the road width, and various things. And we can say what it means to be a valid observation. So obviously we can't assume safety for arbitrary big wind shifts or arbitrary big sensor errors. You have to bound the sensor error. So we just say that it's a, for some, I've done exactly what uses the next sensor error. Quarter of a meter was the next sensor error. And then using this, we can formulate an actor exactly the safety property that we want. But for any sequence of valid observations, then you're still on the road in the final state. And what happens is that you start trying to prove this, and you start trying to prove this, and you do a lot of munging. And because it's actor, we don't have any nice tactics to do this automatically for us, sadly. But what happens is that you come down to the following lemma that you need about the controller. So you iterate on the proof, and then you realize you need this lemma that holds to the controller. So in particular, that if the and I should have said the inputs to the controller are the current sensor reading and the previous sensor reading at the previous time step. And X is the current sensor reading and Y is the previous sensor reading. So if X is less than or equal to the road width plus the max sensor error, and the same for Y, then the absolute value of the controller, the output of the controller plus 2 times X minus Y, has got to be less than the road width minus the max wind chip minus 3 times the max sensor error. And if we can prove that, then we can prove the final theorem. So, I mean, the obvious thing, we want to implement the controller by a neural network. We obviously don't want to write the neural network in actor, and we don't want to be proving about this. I mean, I don't think you could even you couldn't even express the neural network in actor without actor crashing, because how many nodes, zillions of nodes, and it's just not feasible to do. So we can write this spec. So we just have the spec in vehicle is literally just that lemma, right? That's the only lemma that we need to hold. So we formalize, let's just say, there's an input vector, current sensor, previous sensor reading. We say we have some controller, and we say what the notion of safe input was. And here we put in the concrete values for ease, but in active it was slightly more abstract, but they match to the same thing. And then we have exactly the result that we wanted for the safe output. The controller, the output of the controller is plus 2 times current sensor reading minus previous sensor reading is 125. And the property that we want is that for any X, safe input implies safe output. So in this file, in this folder, we also have the ONNX file, which is the actual neural network, trained neural network that you would hope would obey the specification. So what we can do is that we can call verify on this. So generates a specification. So we provide the specification, we provide the network, and we say what verify we want to use, and we also provide this extra argument cache, which is going to create an object that represents the result of a verification. And crucially, what we want, right, is that for the result in actor that we generate to be linked back to the original network, the actual network object, right? And if the actual network object, the ONNX file, changes on disk, we want the proof in actor to invalidate, because otherwise you're going to be type checking your actor file, and if the underlying neural network gets retrained, then and the neural network changes, and your proof in actor is not going to invalidate. So what this cache contains is it contains a hash of all the hash and file paths to all the external resources that your specification has used. And then when actor, we're going to verify this. And then when actor wants to check this verification result, it will go to the cache and it will check, rehash all the external resources, relook for external resources, and check that the proof that have remained unchanged, and therefore the proof still holds. Now, the problem is, in this case, it's very quick, but an alternative approach might be just to re-verify every time Agda, you type check in Agda, but of course, for very expensive verification operations, that's completely going to destroy your workflow. If it takes 8 hours, a big network, it takes 8 hours to perform verification result. Every time you hit type check, it takes 8 hours. So the caching mechanism is designed to work around that, but still guarantee the link between the actual deployed object and the proof network. So as you can see, this network does satisfy this property. We've proved that no kind of example exists. We've actually managed to generate the cache. So given a cache, we can then run the vehicle in export mode. So what we said here is that we want to export the specification and we want to export it to Agda. And that we use this cache, we provide a reference to the cache that we generated, and we want to generate an Agda file. That's a weird error. Warning. Okay. Okay, cool. Will be ignored as confined to Agda. Okay, sure. Right. So what's been generated here is an Agda version of the specification. So we've literally just taken the code and translated it to Agda. The external resources are currently loaded as postulates. In theory, you could write Agda bindings that would actually link this to disk and write an Agda macro that actually validated the neural network. Very painful to do. Maybe if you were going to use this in an industrial strength setting, then you would put the effort into doing that. But at the moment, we just have postulates. But crucially, we compile the property just to an Agda macro that calls out to the verification, that calls the vehicle and asks the vehicle to check the verification cache and returns true or false depending on whether the proof is still valid. And then we can just import this module and fill in. We can use the controller. And we can, and this is the point where I really hope it's going to work. Sometimes it's still, so occasionally it's still a bit flaky about generating when you call back to vehicle. Occasionally we get that input output streams and stuff. Error while running the command vehicle validate cache. Unable to read the verification cache from the file. Does not exist. Okay. Apologies. Demo bring down as always. But assuming that I had named the verification, I think I've named the verification cache the wrong thing in the result. But assuming that I had named the verification cache in the correct name matched up between the export result and not, then this would type check and the whole proof would type check to get the whole thing in Agda. So yeah, and then you have a proof of the system safety and you have a proof from your network, and yet you're not representing, you've managed to avoid representing the neural network in your interactive theorem prover. So you've avoided that performance and representation bottleneck. So we're hoping that there might be some interesting, some non-trivial systems proofs that we can do with this for trying to verify some.
I'm actually interested in examples, so if you want to send us an example, what would be especially problems so that take from the neural network to the whole system verification. None of the easy to find because most examples we find are from neural net verification community. They won't be interested in neural nets. So yeah, if you have examples that I want to explore, we'll be happy to look into that.
I mean, the thing that maybe would be, I mean, it's more of a, I mean, it's more of a PhD project than a kind of master's project, but actually the ACAS-Zoo network, exactly about overall safety, trying to prove that two autonomous drones running the ACAS-Zoo networks actually don't collide ever, would be a perfect example of what we would like to do with this sort of stuff. Yeah.
The road width parameter is that variable, but it's like fixed.
So
I'm not sure if you can have like multiple conflicting properties is valid in specific context. For example, it could be smaller for a city road versus a car going to a highway where you have more leverage.
Yep.
How do you
So in this version, so you notice in Actor we had it kind of in Agda, we had it kind of hard coded. It was abstract, but the values were hard coded here. But what you would do is that you would, in the vehicle specification, if you wanted to do that, you would add some external parameters here. So road width equals rat, etc. You would then write what we wrote in Agda here instead of having plugged in the hard-coded values. And then you could simply pass this in at verify time. You could set different road widths for different verifications. So you could alter the parameters at verification time, and you could see which ones hold and which ones didn't. And then you generate, for each set of verification parameters, you could generate a new spec, a new Agda version of the spec. So yeah, so hopefully it is that the idea was to build it so it really is ergonomic and flexible like that. You really can play around with your verification conditions rather than hard coding them.
I could potentially create a map of city or state into this and the network.
Yeah, you could do, yes. Yeah. It'd be a lot of work, but yes, yeah. Okay, cool. Shall we go to the wrap up slides? So, yeah, so we present the vehicle. It does the whole life cycle of neural network verification, and the pure functional specification language provides the glue that binds it all together. We actually have active formalizations of the translation from the core vehicle syntax down to the verifiers and down to the loss function backends and the proof of soundness for all directions. So we have a proof that actually the verifier semantics actually matches the same semantics that you get in the loss functions. So that's formally verified down there. The compiler itself is written in Haskell and is not formally verified, but we have a verified tiny implementation that shows that in principle that it's sound. And we really hope that it is going to be useful in improving the safety and the trust that we can have in AI systems, at least. And so it's never going to be applicable to ChatGPT or huge image recognition models for general autonomous driving, but for certain domain specific problems, we really think that we can get some formal guarantees about the behavior of these systems. And there is a whole load of possible application areas. As we said, if you have any ideas, please tell us. But we've got people working on intrusion detection systems in networking protocols as malware detection systems. We have tried to do chatbot systems. Often they use subclassifiers to solve small, very small sub-problems in chat applications. So for example, the EU in its wisdom has just passed a law about 2-3 years ago that says all chatbots that when asked to must identify themselves as as a robot, there we go, messing up, as a robot when asked to, right? Now, how do you get a large language model to do that, right? So what often happens is that you maybe have a preprocessor that tries to detect a question are you a robot? and then answer it, and otherwise feed it off to the large language model. So maybe that small verifier, that small neural network is verifiable, whereas the large model is not.
Yeah, what would that look like for, I don't know, like, what would the correctness property look like?
So it's incredibly difficult coming up with the correctness property. So one of the PhD students has been looking at it, and basically the correctness property that we were looking at is a version of robustness, and says that, and what we do is that we have a manually labeled training data set of all the different ways.
So you have a sort of classifier that detects whether or not it's asking this.
Yeah.
If that's robust against.
Yeah, so perturbations, word level perturbations, character level perturbations, and yes, yeah, that's
Yeah, it's sort of like NLP, like perturbing, like a sentence.
Yeah, exactly. Yeah, but of course it brings a whole new set of challenges because images are continuous domain, whereas NLP is really very, very discrete.
Very strange.
Yeah, so you have to really be careful about how you're specifying properties. So that's what our PhD, Cassie's PhD student has been looking into. Obviously, there's physical simulations and then correctness of control systems as well. So on the function programming side, I mean, the expressive type systems are really very useful for this multi-backend system and decomposing your compiler into so that you can reuse the same passes but have different set of types and built-ins. Really is vital. If we were just trying to incorporate this into one monolithic type checking pass and type system that calculated all of them at the same time, the complexity of it would be really very daunting. Whereas if you have it modular and you can read type check with just different set of types, then it works really well. So the PR verification challenges, I think the interesting ones is that abstract interpretation systems, as we discussed at the start, are much more limited in the number of specifications that they can verify. Marabou can verify anything that's linear with existential problems which are linear. They can really only verify input-output relationship problems. But how can we report to the users why their spec does not fall into that problem, given an arbitrary higher order spec? What goes wrong? So can we come up with a type system that will actually generate useful error information in the same way that we can generate for Marabou when we reject the specs?
This might be getting a little too off topic, but I can't even imagine kind of like what a useful abstractor interpreter for like.
Okay, so what the domains would be, or
yeah, sure.
So what happens is that you say. So they take problems with if your inputs are in this range, then your outputs are in that range, or what output range can you reach? And they try and bound the abstract interpretation domains. There's a lot of research into what they are, but high order polytopes or zonotopes or things like that. And then you push them through the network layers, and you try and keep try and clamp down on the error for every. So it's they're definitely the most performant. These are the ones that can do millions of nodes, tens of millions of nodes. They're definitely more performant than Marabou, but at the cost that your specs are much more limited. So you could do ACASU because that's an input-output spec. You could do robustness, input-output spec. You couldn't do the win controller one because if you remember, that related the output of the network to its inputs, and that was a relationship. So
these polytopes basically, you talk about like polytopes of all, like with the SMP based thing, you can talk about like deeper properties.
Exactly. So so there's trade-offs on your verifier. There's trade-offs, and incorporating multiple verifiers would allow you to make that decision rather than just being stuck with Marabou. And actually, so neural network verification is really weird because you don't know what the answer is, and even for what the answer should be, and even for in the competitions, when they have these neural networks, there are millions and millions of nodes, and they're checking whether, for example, they're robust around an input image. You don't know what the answer for your competition is, and these verifiers are famous for giving different contradictory answers. So, and at the moment, it's just usually done by majority voting. or if one is clearly an outlier, then if one says unsat and the rest say sat, then you can check the sat. But if one's but in general, it's very difficult to know what the ground truth is, and it would be really amazing to have a formally verified implementation that it wouldn't have to be incredibly performant, but just enough that you could eventually run it to establish your ground truth for all of these properties, because at the moment the competitions are deeply unsatisfying when the verifiers disagree, because you just don't know the ground truth. Yeah, we're always interested in collaborations, so please reach out, and thank you for coming. Hope it's been useful and interesting.
So this is maybe a little far out of the building, but so when you're like perturbing a sentence, right? Like what's that look like compared? You're looking at the
So in perturbing the sentence, so there's two questions, right? You have the problem, once again, you have the mismatch between the problem domain and the actual input. So your problem space, perturbing it is really quite intuitive. Add words, delete letters, rearrange things. I mean, there's lots of ways you can mess with sentences, and the user's intent is still very clear. You can change synonyms, you can substitute synonyms, etc., etc. Now the question is, how does that map down to perturbations in the embedding space? Because you're mapping down sentences to points in a very high dimensional vector space. And what we found is that you draw an epsilon ball around your embedded point, and you don't actually contain any valid sentences. You may verify it, but there's no other points in your input space is very sparse. Compared to the problem domain is very sparse compared to your input space. So you need some much cleverer way of determining what regions of your input space are going to correspond to useful, that are actually going to capture useful perturbations in your problem space. And we can send you a reference paper if you want, but the short answer is that you embed a load of points in you cluster your points in your training data set semantically, so that they semantically similar sentences. You embed them all, and then you try and draw a hyper rectangle or something around your cluster of points, and then you verify that everything within that cluster is classified correctly.
And by the way, in addition to doing some like structural rearranging and stuff, right? I suppose you could always ask a much weaker model to rewrite a sentence to something.
Yes. Yeah. I mean, we're not sure, but there's some. I mean, it's a bonkersly hard problem actually to solve, because the crazy things like there's crazy inputs. There's example sentences in the data set which are like, oh, did you see the recent episode of AI called "Are You a Robot?" Or there's arbitrary deeply nested semantic embeddings into indirections, this sort of stuff.
Once you were, I think 10 minutes to the lunch break, but Gwen has joined, and since we're still on YouTube, etc., would be nice to switch Gwen, because she was one of the main developers, so she's ready. Gwen, are you ready? Can you hear us?
I can hear you, yeah.
Do you want to?
Is there anything that you would like to add to what we said?
No, I think you've covered it all.
Okay. Well, without Gwen, none of this would have been possible. So, yeah.
Yeah, if you want to briefly switch the video, please do it.
Couldn't make it today, but we really didn't want to avoid cutting any credit.
Yes, certainly.
Okay.
Okay, let's take the discussion to the lunch break.
Yeah.
Thanks, Gwen. Thanks for joining.
Thank you.
Okay.
Hello? Hello, hello? You have your earpiece.
I do.
Can you check on the St. Helens stream of how the audio is and stream it live?
Just give me a minute.
I can do that. No, this is the reason why they don't have we technically test microphone, test microphone, test microphone, test microphone, testing microphone, testing microphone, testing microphone 1, testing microphone 2, testing microphone 3, testing microphone 4, testing microphone 5, testing microphone 6, testing microphone 7, testing microphone 8, test microphone, test microphone, test microphone, testing microphone, testing microphone 1, testing microphone 2,
Yeah, let's do that.
microphone 3, testing microphone 4.
I'll just leave this sign because I've seen one of you.
Yeah.
No.